A very good morning, children. In the last video, we had learned about the homogeneous equilibrium. Do you remember that? Yeah, in the lecture number 3. And now in the lecture number 4, we are going to study about, for example, in a reaction, the reactants and products, if they are present in different phase. We will call such kind of reactions which are under equilibrium as the heterogeneous equilibrium. What do we call them as the heterogeneous equilibrium? Means the reactants and products are not present in the same phase. The reactant may be in the solid state or the product may be in the gaseous state. How many states do we know? How many states of matter do we know, children? How many states of matter do we know? We know generally solids and generally liquids. Here the pure solids are mentioned as small s and the pure liquids are mentioned as small l. But for example, there is some lemon juice. The original juice that we speak, it's called as lemon liquid. But when you dissolve that in water, it is not in a pure state, it is in a compound state. Such kind of solutions we call as the aqueous solutions. Is it not? And one more state of matter we know, that is the gaseous state of the matter. Means gases are also mixtures, they are not present in the pure state. So these are also present in their impure form. Right. Now coming to this third, pure states of matter, either solid or the pure liquid. When we are calculating the equilibrium constant, that is Kc, we will make these pure solid state or pure liquid state of matter as unity because they are considered as constant values. How are they considered as that? These are considered as the constant values in a reaction. Generally, when you are calculating a Kc, how do you recalculate? You calculate the concentration of the products by concentration of the reactants. Is it not expressed to the stoichiometric coefficient? When you are doing so, you will not consider these two states of matter. Which one? Pure solid state and pure liquid state, because their value will be unity. Whatever concentration you take, their value will be unity or their value will be constant. So once again, let's recall what is meant by the heterogeneous equilibrium. The definition we got here like equilibrium in a system having more than one phase. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. So here once you take example number 1, calcium carbonate. It is a solid form. When it is decomposing, it is forming calcium oxide. It is also in the solid state and forming carbon dioxide gas. So here in this reaction, and which is at equilibrium state, forward reaction and backward reaction are also indicated here. What we need to point out is it is a heterogeneous equilibrium reaction. How can we say? Because here only solid is there in the reactant side and the product side solid is there and also gaseous state of matter is there. So such kind of heterogeneous equilibrium systems. When we are going to calculate the Kc, let me say how to calculate Kc for this reaction. Generally, how do you use to give the Kc value? You used to give Kc the product of concentration of the products upon product of concentration of the reactants raised to the coefficient. But what is the point to remember? Whenever there are pure solids or pure liquids, they become unity. In this, we have the pure solid form calcium carbonate and the pure solid form of calcium oxide. So no need to consider their concentration terms. We need to concentrate only on the concentration term other than the pure solid and the liquid. Means we need to concentrate only the equilibrium constant Kc depend upon the concentration of only the gaseous state of matter in this kind of reaction. So Kc, how do we give? Generally concentration of products. Let me write in a simple way. Calcium oxide is the product. It is in the gaseous state. Which state, children? This is in the gaseous state. Upon concentration of the carbon dioxide gas, which is also in the gaseous state, and calcium carbonate, which is in the solid state. Sorry, calcium oxide is in the solid state. So these both are becoming unity. These both are becoming unity. Then our Kc depends upon only the concentration of the gaseous state of matter. Gaseous state of matter. Or if we express in the partial form, pressure. Generally gases will have pressures we have done in the last class. So Kp depends upon the partial pressure of the carbon dioxide gas. Partial pressure of the carbon dioxide gas. So in this session, what is the updated version we have learned, children? Whenever we have pure solid and liquid, we do not want to calculate or take in consideration their concentration term because their concentration term becomes unity. Now can you write the Kc value for the second equation? What is the second example I have chosen here means? Generally we know how to purify the metals. Is it not? Nickel. In the purification of metallic nickel, we pass it over through carbon monoxide gas to form a nickel tetracarbonyl complex. Again from there we can get the pure nickel. So this is method used in the purification of the nickel metal. Now can you write Kc for this equation, children? Kc. Once study the reactants and products here. Reactants are nickel is in the pure solid state, carbon monoxide is in the gaseous state, whereas nickel tetracarbonyl, that is the product, that is also in the gaseous state. What we had learned, when there are pure solids or liquids, they become constant. Now how can we write our Kc? Concentration of products upon concentration of the reactants that are only in the gaseous state or in the aqueous state. So here Kc, what are the products we got? Nickel tetracarbonyl, that is in the presence of gaseous state, upon carbon monoxide gas raised to the power of its stoichiometric coefficient. Here the coefficient is the 4. Now I hope you understood how to work for the heterogeneous equilibrium systems. One more example we got. Silver oxide, which is in the solid form, is reacting with nitric acid, which is in the gaseous form, to give silver nitrate, which is in the aqueous form, and water, balancing purpose. How shall we write Kc for this reaction, children? How shall we write Kc for this reaction? We need to give out the solids and we need to give out the liquids, because in the pure form their value will become constant. So in the products, what do we have? We have silver nitrate and the aqueous state. So concentration of the silver nitrate in the aqueous state raised to some coefficient. What is this coefficient? This equation we got 2. And how about the remaining part of the reactants? In the reactants we have nitric acid, HNO3, that is in the gaseous form, raised to the power 2. I hope you understood how to write equilibrium constant for the heterogeneous systems. Now let us relate something between the Kp and Kc values under the homogeneous systems. So please write down these examples, student. Now we will go for the relation between Kp and Kc for the homogeneous systems. Now let us say the relationship between Kp and Kc, few reactions. In the last class, do you remember this equation, children? Which equation? How is this Kp related to Kc? Kp is equal to Kc into R into T to the power of delta Ng. What is delta Ng? It is the difference in the number of moles of gaseous products minus number of moles of gaseous reactants. Number of moles of gaseous products, number of moles of gaseous products minus number of moles of gaseous reactants. Yes or no? So let us see how to relate this Kp and Kc for few reactions. Let us take one of the reaction. Hydrogen gas is reacting with iodine gas, which is at equilibrium with hydrogen iodide gas. Okay. Now let us see how to calculate delta Ng. Here how many number of moles of products are there on the gaseous state? 2. Yes or no? Number of moles of gaseous products. How many are there? 2. Minus number of moles of gaseous reactants. Here 1 mole of iodine is there. Here 1 mole of hydrogen is there. So total 2 moles of reactants are there. So how shall we get delta Ng? Delta Ng is equal to 0. 2 minus 2, 0. So how can we apply here? Generally we know Kp is equal to Kc into RT into delta Ng. Anyhow this becomes 0. So Kp is equal to Kc into RT to the power of 0. So this term is becoming 0. Now Kp is equal to Kc. Kp is equal to Kc. Or shall we bring one conclusion here? What the conclusion we are bringing? Delta Ng, when it is equal to 0, Kp will be equal to Kc. This is the first condition. Let us take one more example, then we shall calculate. Example number 2. Phosphorus pentachloride gas, on decomposing it is giving phosphorus trichloride gas and chlorine gas. Here, how many number of moles of products are there of the gas? This is 1 mole, this is another mole. 2 moles are there. And here, only 1 mole of gaseous reactant is there. So delta Ng, how will you calculate, children? 2. Here 1 mole, here another mole of the gaseous products are there. Here 1 mole of reactant is there. 2 minus 1, we have 1. Now delta Ng, how much we got? 1. Or shall we write Kp is equal to Kc into R into T to the power of 1. Means Kp is the product of Kc into R into T. Means if these two are multiplied, then we are getting this value. Or shall we say Kp is now more than Kc? Kp is more than the Kc. If two are multiplied, they are equal to Kp. So we say Kp is equal to, Kp is greater than Kc. Or shall we speak like when the delta Ng is greater than 0? When the delta Ng is greater than 0, we can relate Kp is greater than Kc. Kp is greater than Kc. Let us take one more equation. What equation shall we take here, children? Like nitrogen gas is combining with hydrogen gas to form ammonia gas. What to form? Ammonia gas. Here delta Ng. How many number of moles of products are there? 2 moles are there. So 2 minus. Here 3 moles of hydrogen is there, 1 mole of nitrogen is there. So totally 4 we got. So delta Ng is equal to minus 2. Delta Ng is equal to minus 2. Or shall we say Kp is equal to Kc into R into T to the power of minus 2. Or shall we write Kp is equal to Kc upon Rt to the power of 2. To the power of 2. Or shall we say Kp is going to multiply with R into T, that is equal to Kc. Or we can say this both product is equal to Kc. Or shall we speak Kc is greater than Kp? No? Kc is greater than Kp. So when the condition number 3 you take, when the delta Ng is less than 0, minus 2 you got. So shall we relate Kp will be less than Kc? How shall you relate? Kp is less than Kc. So this is how, by knowing the difference in the number of moles of reactants and products and reactants, we can bring a relationship between the Kp and Kc. So let's conclude here. When the delta Ng value what we got is equal to 0, Kp is equal to Kc. When the delta Ng value what we got is greater than 0, Kp is greater than Kc. When the delta Ng is less than 0, Kp will be less than Kc. So this is what a relationship between Kp and Kc for some reactions we have learned. So let's take up the next topic. Let us see a problem or numerical on this conceptual and relating Kp and Kc. What is the question given here? Question given here is, for equilibrium, 2 moles of NaCl are forming 2 moles of NO gas and Cl2 gas. The value of equilibrium constant Kc is 3.75 into 10 power minus 6 at temperature. Where is the temperature mentioned here? Let us see the temperature that was mentioned here. 1069 Kelvin. 1069 Kelvin. Calculate the Kp for the reaction at this temperature. Calculate the Kp for the reaction at this temperature. So what was given in this question? Kc was given and temperature was given. We already came to know about the formula about relation of Kp and Kc. Kp is equal to Kc into R into T upon delta Ng. Delta Ng. Is it not? Here now let us see how to calculate delta Ng. Number of moles of gaseous products minus number of moles of gaseous reactants. How many moles of gaseous products are there? 2 moles of NO is there and 1 mole of Cl2 is there. Totally 3 moles of gaseous products are there. And 2 moles of gaseous reactants are there. 2 moles of gaseous reactants are there. So shall we say 3 minus 1 is equal to 3 minus 1 is equal to 2. So we substitute the 2 value and now let us apply the calculate Kp. We need to calculate the Kp. What is the Kc value given? 3.75 into 10 power minus 6. Right. This is Kc value into. What is the R value? We know 0.0831. What is the temperature given? Temperature given is 10 to the power 1069 Kelvin. 1069 Kelvin to the power of 2. So once you substitute all these values, you can get the Kp value. In this method, you can apply for the problems given to you. In the next session, we will bring what is the importance of the equilibrium constant. Thank you, children. Have a nice day.